Okay, that says it's working, but nothing. There we go. Okay. Well, that's working. I don't know about other than that. All right. Keep going. 26 is 50 degrees. 28 is 40 degrees. 30 is 50 degrees. 32 is 3 feet 3 inches. And then all the descriptions of how you got there. 34 is a proof. And 36 is a proof. 38 is on the other page. Whoops. What? We only went to 36. What? Did we only go through 36 or did we go through 38? What? 32? Well, then why am I still reading? Okay. What questions do we have? 24. Oh, I don't know what happened to my black marker. Disappeared into the ether. What? That's very confusing, but I'll answer that later. Okay, 24 you said? Okay. Graph each quadrilateral with the given vertices, determine whether the figure is a rectangle. Justify it with the method. Q is -2, 2. And R is 0, -2. And S is 6, 1. And T is 4, 5. And we're supposed to use the distance formula. So you can do a better job graphing it, but it's at -2, 2, and at 0, -2, and at 6, 1, and at 4, 5. Something like that. That's not it at all, but you get the idea. Right? So, we're supposed to determine whether the figure is a rectangle using the distance formula. So what distance-related things do we know about rectangles? The sides, true enough. So if the sides, the opposite sides are congruent, then it's a parallelogram, at least, right? So we need one more thing to make it a rectangle. If it let us use the angles, then we could try to come up with something with that, right? We could see if they were perpendicular, so see if their slopes are opposite reciprocal. But it wants us to use the distance formula, right? So what other thing do we know about rectangles? They're diagonals. That's true. What do we know about their diagonals? They are congruent. The zipper is dying. I'm going to get stuck in this jacket. I don't know what's happening. They are congruent. So if we can prove that this is congruent to this, and this is congruent to this, and this is congruent to this, then we've got this, right? So what is the distance formula? Let's start with that. Add y2 minus y1 quantity squared. All right, so QRST, something like that, right? All right, so the distance between, that even right? Probably need to graph it slightly better because my brain is having trouble seeing what's happening. 1, 2, 1, 2. This is Q, 0, -2. I think I graphed that one wrong. I think that's part of what's happening. This is R, and then 1, 2, 3, 4, 5, 6, 1. This is S, and 1, 2, 3, 4, 1, 2, 3, 4, 5. This is T. There we go. Now we can see what's happening, right? So we need to find the distance between Q and T. And just start plugging stuff in, right? We don't really even have to get the square root. We don't have to reduce the square root. Probably don't even know how to do that yet. Cover that more in Algebra 2. So we just need to know what's inside, because if it's the same as the other side, then we're on our way, right? So distance between Q and T. What are we going to put right here? Okay. What about this one? 4. And what about this one? 2 and 5. So -2 minus 4 is signs are the same. -6. What's -6 squared? 36. And then 2 minus 5 is -3 squared is 9. So it's square root of 45. Excuse me. Which we could reduce, I think. Yeah, but we don't care. And so that's QT. So we need RS is the one opposite that. So we can plug that stuff in there. Okay. So S, we've got 6. And R, we've got 0. And then for the Y's, we've got 1 and -2. What's 6 minus 0? 6 squared is 36. 1 minus -2, we got a ka-chink. That's 3. Squared is 9. We can already tell this is fine, right? That works. Then you do the same thing for QR and TS and RT and QS, right? That makes sense. Mm-hmm. Yeah, the main tricky mental thing in that problem is that you have to find the distance of the diagonals, right? It's not necessarily a hard problem, it's just kind of tedious, which is true of a lot of these coordinate ones. What other questions do we have? What? 20. Okay. Given it's a rectangle, we got to start proving triangles are congruent. Sounds fine. We are given that A, B, C, D is a rectangle. Okay, so all the things that are true about rectangles are true about it. We want to prove that triangle ADC is congruent to triangle BCD. So ADC is this one. So prove that one is congruent to this one. So we need stuff about those triangles, and then we need one of our proofs of congruence, right? Side, 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 side angle, side, etc. So, what can we say? Okay, so the sides are congruent. So specifically, which sides? AD and BC, sure, sounds great. AD is congruent to BC because opposite sides of a rectangle are congruent. Right? So we just said this is congruent to that. So we've got an S. What now?
Each corner is 90 degrees?
True. True enough. So ADC and BCD are right angles. Angle ADC and angle BCD are right angles. True enough. Oh, because definition of rectangle. Okay. So we said this is a 90 degree and that's a 90 degree. What else? AB, it is. However, AB is in a totally different triangle. So we could say it, but I don't know if it's going to help us. Do our triangles share anything? Okay, what do they share? Which side? They totally do share a side. You're totally correct. And yes, it is DC. So we could say that DC is congruent to CD. What lets us say that? What's that called? It's the mirror one, right? What do you do in a mirror? What does a mirror do? It reflects. So the reflexive property. Reflexive. So this is congruent to itself. What else? Your side angle side. So technically, no, we don't yet, but we basically do. And if you wrote that at this point in this proof on a test, I probably wouldn't count off. Technically, we have to say that this angle is congruent to that angle. We haven't technically said that yet. ADC is congruent to angle BCD. Well, let's us do that. What? We said they're right angles. So now we said they're congruent. What? There's a theorem. I think it's a theorem. It might be a postulate. I'd have to go back and see. That says all right angles are congruent. I feel like it's got to be a postulate because it's like one of those no-duh kind of statements, right? So now we do have side angle side, triangle ADC is congruent to triangle BCD because of side angle side. By the way, if this was a little different, we'd have to be given different stuff to get there. But if we weren't told this is a rectangle, you could potentially prove it was a rectangle by proving just what we proved, that this is congruent to that. And then you could use CP/CTC to say that their diagonals are congruent, which means it's a rectangle, right? What other questions do we have from this lesson? Okay, let's do the next lesson about rhombuses and squares. What? I have a quiz to get back to you. Let's see. Do I have a quiz to get back to you? Let me look in my graded folder. And in my graded before the folder chunk. Let's see. Your name isn't Donovan or Matthias or Paisley or Katie or Reese. So you're not any of those people. Let's look in here. Your name isn't Fix. Oh, wait, that's not somebody's name. Oh, look, your name is Mia. That is one of your names. Bam. And that. Ooh, excuse me. All right. So, a rhombus. What is a rhombus? If you learned about rhombuses in middle school, it's possible, you may not have, but it's possible. If you did, somebody probably told you the lie that a rhombus is a squashed square. Because that's not what a rhombus is. Because a square is also a rhombus. So what is a rhombus? A rhombus is a parallelogram with two pairs of congruent sides. In other words, all four sides are congruent. Right? But it doesn't have to be, not all, it's kind of like all rectangles are parallelograms, but not all parallelograms are rectangles, right? You can have a square, which is a rhombus, that has not only equal sides, but 90-degree angles, makes it a square, right? So it's the full definition for a square is a parallelogram with four sides congruent and all four right angles, right? So you could have a short definition of a square, or shorter, that it's a rectangle with all four sides congruent, right? Or it's a rhombus with all four angles congruent. Making sense so far? Okay, so there are a couple of theorems with rhombi, which is the plural of rhombus, even though rhombuses sounds more fun. They didn't ask me. Excuse me. So the first one is, if a parallelogram is a rhombus, then its diagonals are perpendicular. So if we have a rhombus like this, he has diagonals that are perpendicular. The other theorem with rhombi, word is annoying, it's fine, is quite useful, and that is that the diagonals bisect each other, right? Which is very useful. Let's do a couple guided practices. Let's do guided practice 1A on page 431. So we're supposed to use the rhombus above, which looks like this, more or less, has diagonals drawn, has the vertices F, G, H, and J, and the diagonals intersect at K. And for guided practice 1A, it says if the measure of FK equals 5 and the measure of FG equals 13, we want to find the measure of KJ. Right? So if I was doing a problem like this on a deal, I would draw the little sketch real quick, right? And I would label the stuff on my paper. I would pretty much always do that if it doesn't really provide it for me. So we've got FK, so that is this one right here. This one is 5. And FG is this side right here. And it is 13. So this is 5 and this is 13 in this problem, right? And we're supposed to find KJ. We're supposed to find this one. So, what useful pieces of information do we have for this problem? We've got triangles, we've got a rhombus. So the useful thing to keep in mind with this problem is that a rhombus is also a parallelogram. So he has all the properties of a parallelogram, right? So we've got diagonals and we've got sides. What's true about the diagonals of a parallelogram? Y'all remember? They're not always congruent. If it's a rectangle, they are. If it's a rectangle, they're congruent. There's something is congruent about them, though. What do they do to each other if it's a parallelogram? What? They bisect each other, which means that this side that we're interested in is the same as this side, right? Also, since it's a rhombus, this is a 90-degree angle. So if we find this one, then we'll have our answer, right? So we have two sides of a right triangle. How can we find the third? Pythagorean theorem. That's true. What is the Pythagorean theorem? Yes, it is. A squared plus b squared equals c squared. Which ones are we going to put numbers in? A and what else? No, not B. How do I know it's not? How do I know which one is C? That's the one that really matters where it goes, right? Which one is C always? What's the name for that side of a right triangle? It's this one right here. What's unique about that one? It's the longest side is one way of thinking about it. It's called the hypotenuse. So it's the longest side. Sometimes it's hard to tell which is the longest side. So it's also the one across from the 90, right? So that's this 13 one, right? All right. So what's 5 squared? 25. What is 13 squared? What's your calculator? Ethan, I don't know. That's crazy. $169. Then we would subtract the 25. Eesh. So b squared would equal 144. Now how do we get rid of the squared? What? Square root. True enough. We take the square root of both sides, we get plus or minus, but we're going to throw out the minus because we're talking about distance, so we're going to absolute value it. And the square root of 144 is 12. So this is 12, which means this is the one that we're looking for is 12. Easy peasy. All right, I want y'all to do guided practice 1B. Ready, go. I'll get started on that. I'm going to use the restroom. I'll be right back, and then I'll show you the solution. The mic and the streaming are on, so don't say anything rude. So, for guided practice 1B, the measure of angle JFK is 6y plus 7. So, JFK is this angle right here, right? So that's 6y plus 7, right? And then angle KFG, this one right here, is 9y minus 5. We learned today that in a rhombus, the angles are bisected, so we just set these equal, right? So 6y plus 7 equals 9y minus 5. We subtract 6y from both sides. We end up with 7 equals 3y minus 5. Then we add 5 to both sides. End up with 12 equals 3y, and then we divide by 3 and end up with y equals 4. Easy money, easy money. All right. Okay. A square, we already said, is a rhombus with all 4 angles equal. All 4 angles are right angles, so it's a quadrilateral with, it is a parallelogram. It is a quadrilateral. Quadrilateral is just this 4-sided figure, right? So but it is a parallelogram with 4 congruent sides and 4 right angles. Easy peasy. There are 3 more theorems. These apply to rhombi and squares, both. First 2 are the converse of the other 2, right? So if the diagonals are perpendicular, then the parallelogram is a rhombus. If one set of diagonals, let me write it down. Right? If one pair of angles is bisected by a diagonal, then it's a rhombus. Then the parallelogram is a rhombus. So you don't have to get all of the groups. For it to be a rhombus. I'm sorry, because my brain is thinking, is that even? I know it literally says that in the book, but if one diagonal of a parallelogram bisects a pair of opposite angles, then the parallelogram is a rhombus. I feel like, unless it's a kite, because the kite also bisects it. And because a kite, are we beefing with the book right now? Oh, but a kite isn't a parallelogram. There we go. We're not beefing with the book. I figured it out. My brain got confused. Almost had a stroke. Yeah. If a parallelogram has a diagonal that bisects both a pair of side angles, then we've got a rhombus, right? So the last one, or the last couple, are kind of new. Those two are just the converses of the other ones that we had before. But Theorem 619 says if one pair of consecutive sides of a parallelogram are congruent, then it's a rhombus, which is nice because if we know it's a parallelogram, right, then definition of a rhombus says that they're all congruent, right? But this theorem says that if we can just prove that a couple of consecutive ones, so these two or these two or the top two or whatever, right? If we can just get a couple of them proved, then we can prove that the whole thing's a rhombus, which is nice, can save us some steps, right? The theorem 620 is kind of the one that I already said. It's one of those theorems that's almost a no-duh statement, but if you can prove through whatever method that a quadrilateral is a rectangle and you can prove it's a rhombus, then it's a square, right? Which can be useful. Okay, let's see if we can squeeze. Let me go ahead and give you your homework, and then we're going to go ahead and squeeze in guided practice 4 at the bottom of page 434. Your homework is on pages 435 and 436, and we're going to do numbers 8 through 30 evens. All right, so we don't have a lot of time. We may push our time some. If you need to leave right at 10, that's fine. Mike can do it in 5 minutes. We'll see. So we are given that J is at 5, 0, and K is at 8, -11, and L is at -3, -14, and M is at -6, -3. We're supposed to determine whether the parallelogram is a rhombus, a rectangle, or a square. It could be all of it could be more than one, because if it's a square, then it's all the other ones too, right? So, get a little bit of a graph for this. So we're at 1, 2, 3, 4, 5, 0. We're at 1, 2, 3, 4, 5, 6, 7, 8. I don't know why I'm counting up on the y-axis. That doesn't make any sense. 1, 2, 3, 4, 5, 6, 7, 8, -1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So right there, -3, 1, 2, 3, -14, so 11, 12, 13, 14, so right there, and -1, 2, 3, 4, 5, 6, -1, 2, 3, so something like this. So this one is J, this one is K, and we've got L and M. Okay. So, in order to prove any of those things, what do we have to do? What makes something a rectangle or a square or a rhombus? Sides are congruent. So we'd have to use the distance formula. I'm not necessarily going to walk through all of those things because we practiced the distance formula at the beginning of class, right? So we'd have to find the distance between M and J, right? So we'd start plugging stuff in. Squared plus this is the x's. So M, we've got -6, and J, we've got 5, and for M, we've got -3 and 0, right? So we get the square root of -6 minus 5 is 11, squared is 121. And then -3 minus 0 is -3, squared is 9, so plus 9, so this equals the square root of 130, right? You do that for all the sides, right? If just opposite ones are congruent, then it's a rectangle. If they're all congruent, then we need to check one more thing. I think this turns out to be all of them. Let me see. Yeah. So this turns out to be all of them. So we need to know, what we need to know is, actually, if they were all, what was I going to say? Oh, if opposite sides were congruent, that just means it's a parallelogram, right? So that's not enough. We need to be, in order to tell whether it's a rectangle or square, what's the one other thing that we need to find out? Angles, if they're right angles. If they're right angles, if they're perpendicular, what's true about their slopes? Same if they're parallel, which we know they are because it says it's a parallelogram. So we know that this has the same slope as that, but what about if they're perpendicular? What's true about their slopes then? Yeah, minus switch, that's right. So it's opposite reciprocal, it's flip and flip, right? Right. So we need to know the slope formula. What's the slope formula? What? M equals, got that part. You're in the right vein, but you had the wrong thing, because it's rise over run, right? Which one is rise, the X or the Y? The Y. So it's y2 minus y1 over x2 minus x1, right? So if we were trying to find the slope between M and J, we would do M equals, and y for that, so it'd be -3, and for J it'd be 0, and then the x's, -6 and 5. -3 minus 0 is -3. -6 minus S5 is -11, so it's 3/11ths. Right? So this one has a slope of 3/11ths, which means this one has a slope of 3/11ths. So we know this is a parallelogram. And actually I didn't even think about that until just now, but they tell us this is a parallelogram, which means we know that MJ is the same length as LK. Right? We know that ML is the same length as JK. So really we only need to find one set of them, right? So if we can find MJ and it's congruent to ML, then it's a rhombus, right? Then if we prove that one, and also we have the theorem that says if one of them's a right angle and it's a parallelogram, then they're all right angles. So really all we have to do is do, so we just did MJ. If we do ML, which let's go ahead and do that real quick. So this is the slope between MJ. The slope between ML is either going to be -11/3 or we made a mistake or the key's wrong, right? Those are our options right now. All right, so M and L, for M we've got -3, and L we've got -14. Excuse me. And for the X part, we've got -6, and for L, -3. We could chink these and these. -3 plus 14 is 11. And then -6 plus 3 is -3. So -11/3. That's a right angle. They're right angles because they're opposite reciprocals. We'd have to do one more check and we'd be done. Right? We found this distance. We'd have to find either this distance or this distance. As long as it matches that, we've got all of them. So we would list square, rhombus, rectangle. All right. I think that we're a little past time. Good to go. See you Thursday.